Last video we talked about how to create a time delay using the timer. So now we have a question. In the previous example, calculate the amount of time delay in the delay subroutine generated by the timer. Assume the crystal frequency is 11.0592 megahertz. So the previous question is the last one we discussed. So what did we do here? In this particular delay, we started the timer using setBTR0. So when you start the timer, you had previously loaded it with a particular value FFF2. So it will start to, the timer will start to count from here till FFFF, and after counting till FFFF, when another clock pulse comes in, it will count 0000, then TF will be equal to 1. When TF is equal to 1, this jump if no bit is becomes false, so that it will go to the next instruction, that is clear TR0 and clear TF0, and then return to the main program. So this is the delay program. Okay, so in this delay program, you need to calculate the delay, assuming that 11.059 is the clock frequency, crystal frequency. So we also know that the frequency of the timer is 1 by 12 the frequency 11.0592. So we know the timer frequency, that is 921.6 kilohertz, and sorry, that should be 921.6, okay, kilohertz, and as a result the clock has a time period of t equal to 1 by 921.6, that is 1.085 microsecond. Okay, so we have the time period of one clock period. So from FFF, it will start to count, and it will count up to FFFF, and also it will count one more pulse, which is 0000. Only when it goes from FFFF to 0000 will TF be equal to 1, and only when TF is equal to 1 will it come out of the loop. So that 0000 should also be taken as a count. So what is the total number of counts you can calculate? That is FFFF minus the initially loaded value. The final value is always FFFF. So that minus the initially loaded value plus that 0000. So plus 1. Okay, you have an extra count which is for the 0000. So it is always FFFF minus the initially loaded value plus 1. So that is the total number of counts. So total number of counts into 1.085, which is the time period. So that will be the resulting delay. So that is what is shown here. This minus this the initially loaded value. So that is 13. You can just subtract and see. You can either do it in hex, the hex subtraction, or you can convert each of these to decimal and then subtract whatever. So it is 13 in decimal, and I told that 0000 is also taken because only then TF will be equal to 1. So that is why you are taking this extra 1. So it is totally 13 plus 1, 14 counts. into 1.085 microsecond. So the total time delay is 15.19 microsecond for half the pulse. For the entire period, it is 2 into 15.9 microsecond. So what is the general rule? You have an initial value loaded. Okay. So in these cases, you are not considering how many machine cycles it takes for a particular instruction to be executed. That particular thing is not taken here. Okay. In this case, we are only taking the counter values, the timer values. So initially, the timer was loaded with a particular value THTL. FFFF minus that initial value plus 1 for the 0000. So that is the total number of counts. That into 1.085 microsecond. 1.085 microsecond, how do you get? It is the clock frequency, the crystal frequency divided by 12. You'll get a frequency. 1 by that frequency is your time. So if in the question they change the value of 11.080592 megahertz, you can just divide it by 12. You'll get a frequency and take the reciprocal of that. You'll get the time period. That time period into the number of counts. You know how to get the number of counts. Number of counts is the FFFF minus the initially loaded value plus 1. That answer into 1.08 microsecond will give you the half period. For the entire period, just multiply it by 2. So that is the time delay generated by the timer. So that is a general way of putting it. So you can either compute it in hex or in decimal. If you're computing it in hex, then it is FFFF minus the initially loaded value. Here they are generally putting it as YYXX plus 1 into 1.085 microsecond, where this is the initially loaded value. So this is also in hex. Okay. And if you are taking it in decimal, then convert the initially loaded value to decimal, then 65536 minus that value, that decimal value, into 1.085 microsecond. Okay. So that is how you compute the delay. Now in the next question, so in the previous question, the one we discussed just now, the frequency of the square wave generated, calculate the frequency of the square wave generated on P15. So suppose this is my program. So in the previous question, I told that we did not compute, we did not see the machine cycles or anything. We just took the count. So that is what is told here. The overhead due to instruction in the loop is not considered. So if you want to get a correct exact time delay, that should also be taken. So for that, you're writing the cycles, number of cycles for each instruction, calculating the total number of cycles, and 2 into this value into 1.085 microsecond. That will give you the time. And 1 by this will give you the frequency. So this is with the machine cycles. So with the machine cycles, this is the time. With just the count, this is the time. Same question. Next question is, find the delay generated by timer 0 in the following code using both methods of 9-4. Do not include the overhead due to instruction. So you needn't write the number of machine cycles for each instruction. That needn't be considered. You have a program here. So you just find out what is the initially loaded value. You know the final value will be FFFF. Find the difference, plus 1 into 1.08 microsecond. That will give you the half the period, into 2 will give you the full period. So what is the initially loaded value? It is B8 TH first, then TL. So B8 3E. So B8 3E is the initially loaded value. So how will you find the count? FFFF minus B8 3E plus 1. So you'll get the difference or the number of counts. This is in hex and the same value in decimal. And that into decimal into 1.085 microsecond will give you the time delay. Okay. So similar thing. This is computed in decimal. TH minus TL is 47166. So 65536 minus 47166 18370 into 1.085, the same value. So just understand the logic, how to compute the delay, and you can compute it for any program. Modify TL and TH in the previous example to get the largest time delay possible. Find the delay in millisecond. If you in your calculation, exclude the overhead due to instructions in the loop. Exclude the overhead due to instructions in the loop means what? Do not take the machine cycles. So in this particular case, largest time delay possible is computed. Okay. So what is the initial value that is loaded into THTL? There no such count, no such value is given here. You have to find the largest time delay possible. For that, modify TL and TH. So the time delay will be increased when that counts is increased. So what is the maximum possible counts? If TH and TL is loaded with 0 initially. That is 0, 0, 0, 0 to FFFF. If it counts, that's the maximum possible number of counts. Okay. So that is why we are loading it with TL0 and TH0 with 0. And so 0, 0, 0, 0 to FFFF. So the total value is 65536 and the delay is 71.1065 milliseconds. It generates a square wave on P15 continuously using the timer 1 for a time delay. Find the frequency of the square wave if crystal frequency is given. In your calculation, do not include the overhead. So the initial value in timer 1 is 7634. Final value we know FFFF minus 7634 you'll get a value plus 1. You'll get the counts. The count, you convert it to decimal into 1.085. You get the time delay for half the square wave. Into 2, you'll get the full frequency. Full time period. 1 by the time period, you'll get the frequency. So that is some of the programs to calculate the time delay when you are going through mode 1 programming. Calculate the values to be loaded into TL and TH registers. Look at the following example. So crystal frequency is given. Find the value of TL and TH registers. So the desired time delay is divided by 1.085 microsecond. So TH and TL we need to find out. So time delay is what? Time delay is FF minus THTL, that value plus 1. You get a hex, convert that to decimal, multiply with 1.085 microsecond, that value into 2. That is the time delay. So from that, you know the time delay. Suppose you want to find THTL value. So you can just do it and see. So desired time delay is divided by 1.085 microsecond. Then 65536 minus n, where n is the decimal value we got in the first step. Convert the result of step 2 to hex, where YYXX is the initial hex value to be loaded into the timer's register. Set TL equal to XX and TH equal to YY. So this is the algorithm to find the TL and TH values. So crystal frequency is given. What is the value we need to load to the timer's register if we want to have a time delay of 5 milliseconds? So we can apply the previous algorithm. Time delay we know. So if you know the time delay, what should you do? Time delay divided by 1.085 microsecond. So you'll get a count 65536 minus that count. You'll get a value, convert that to hex, and then separate it to TH and TL. The higher order 8 bits, you'll put it in TH. Low order 8 bits, you'll put it in TL. So that is what is here. Then you can write the program by putting this value EE and 0. Write a program to generate a square wave of 2 kilohertz frequency on P15. So 2 kilohertz frequency. So the time will be 1 by the frequency, that is 500 microsecond. 500 microsecond. So half of it is for high and half of it is for low. So 250 microsecond each for high and low. So 250 microsecond divided by 1.085 microsecond. You'll get a value, convert, subtract it from 65536, convert it to hex and separate it to TL and TH. And you can put it in the program. Again here the frequency has been changed, 50 kilohertz. So T is equal to 1 by 50, 20 millisecond, that is the period. Half of it is 10 millisecond. 10 millisecond divided by 1.085 microsecond. You will get a value, subtract it from 65536. You will get a decimal value, convert it to hex, and then separate it to TL and TH and put it in the program. So here find the time delay in seconds, exclude the overhead. So TLTH value is 0108 is the initially loaded value. So we know it is TL, TL 0108, and 65536 minus this value, you'll get, multiply it with 1.085 microsecond. So in this question, you are doing it for not 3. Decrement and jump if not 0 R3 to again. So you are doing this loop, you are executing this loop for 200 times. So once this delay execution, it will take 70.820 millisecond. 200 times, that multiplied by 200. So this is the total